Hello students, in this class we are going to study the important topic, that is electronic configuration of elements. See, in an atom of an element, the electrons are moving around the nucleus in orbitals, and these orbitals are divided in subshells which have orbitals, and the electrons are filled in orbitals of subshells of atoms of an element in ascending order of energy. Means the first electron goes to the orbital which has the least energy, and when it is filled, then it goes to the orbitals and subshells of higher energy. Then there are four subshells. They are called S, P, D, F, and if we distribute them, if we arrange them in energy wise order of these, are S has the least energy, and P has more energy than the S subshell, D has more energy than the P subshell, and F has the maximum energy of all the subshells. Now we will see that how the electrons are arranged in these four subshells in all the elements. See, there are four subshells. One is S, second is P, third is D, fourth is F. So, arrangement of electrons in these subshells, we say that it is the electronic configuration of an element. And now we will see that how the electronic configuration is written and how the electronic configuration of an element is determined. Now first we see that these are subshells, and in all these subshells, S has number of orbitals as 1, P has 3 orbitals, and D has 5 orbitals, F has 7. So maximum number of electrons that can be accommodated in these number of orbitals, every orbital can accommodate 2 electrons. So maximum number of electrons that an S subshell can electrons, 2 electrons can occupy S subshell, and here it can be maximum number of electrons that can fill the p orbital, that are 6, and here maximum number of electrons are 10, and here 7 into 2. F orbital has maximum number of 14 electrons. Now this is symbolic diagram. If we can show this by this is one orbital, symbolic representation. This boundary is one orbital, and here the arrows shows 2 electrons, and these electrons are having opposite spin. So one we have shown upward and upward arrow, and the second is downward arrow. So they are opposite spin. One is clockwise and another is anti-clockwise. And here there are 3 orbitals, and we can show these orbitals as 1, 2, and 3. So there are maximum number of 6 electrons, 1, 2, 3, 4, 5, 6, that can be accommodated in p subshell. And here there are 5 orbitals. 1, 2, 3, 4. 1, 2, 3, 4, 5, and hence 10 electrons can be accommodated. Each pair of electrons have opposite spin. And here there are 7 orbitals, and 14 electrons are arranged in these 7 orbitals. Let me draw it. Here are 7 orbitals shown by these boxes, and each box represents one orbital, and each orbital can accommodate 2 electrons each. See, in these orbitals, suppose this is D subshell, then first the electrons will occupy, first electron will go to this orbital, the second will go in this orbital, third will go in this, and fourth will go in this, and fifth will go. Then sixth will be pair with this electron, and seventh will pair with this electron, and so on. So this is called Hund's rule, and which every orbital in a subshell first filled with first is singly occupied, and when all the orbitals are singly occupied, then they are paired up. This is called Hund's rule. Now we come on to the how we determine electronic configuration. So there is one Aufbau diagram. Aufbau diagram which shows that how the subshells, they are divided into energy wise distribution. So there we write here S, P, D, F. These are 4 subshells, and S can accommodate 2 electrons, P can accommodate 6, D can accommodate 10, and F can accommodate maximum 14 electrons. Now we write it in this way, that first S, P, D, F. This is the simple trick to determine the electronic configuration of an element. How we determine that? First we write SPDF in this manner, and here we write 1, 2, 3, 4. Now here, see, we write here the name of subshell in reverse order. First S, then PS in reverse order. PS and then again PS. Repeating, and then D, PS, DPS, and again repeating DPS. Then FDPS in this reverse direction. FDPS, F fourth, in the fourth row, FDPS, and then again FDPS. Is that right? First row S is repeated because only S was written, and in the second row PS and PS is written twice. Third row DPS in this direction, and that is written twice, and in the fourth row FDPS, and that is written again twice. Now we number We have written it in order. Now we have to number these subshells. How? It is first we complete the number of s orbitals: 1s, 2s, 3s, 4s, 5s, 6s, 7s, and 8s. Okay. Now we write the number of p, 2p here. Then we start from 2. Here it is 2p, then it is 3p, it is 4p, then 5p, then 6p, then 7p. And again for we write number of d, 3d, then 4d, then 5d, then 6d. Then we write number of f, 4f, 5f. Okay. Now this is the order. This is the least energy. This orbital has least energy. Then it is more than this 1s. Then we come to 2p, then 3s, this 3p, 4s. This is the order of the energy increasing in this order. These are the ascending order orbitals energy. And first the electron goes to this orbital, then this, and then this, so on. Now we will say that how the electrons are arranged, and how can we determine electronic configuration. For electronic configuration, we have to know the number of electrons in an atom, and number of electrons is equal to atomic number. So we have to first see that what is the atomic number of an element. Suppose we say that we have to electronic configuration of boron. इसका atomic number of boron is 5. Then how can we say that 1s2, 2s2, and 2p1? It will be 1s2, 2s2, and 2p1. So this is the electronic configuration of boron here: 1s2, 2s2, 2p1. So in this order we can calculate determine what is the electronic configuration. Now with this electronic configuration we can say that the number of electrons in outermost orbit is 3. Here 2 is the maximum number, and in this second subshell we have 2 plus 1, 3 electrons. So we say that in outermost orbit of boron there are 3 electrons. Okay. And what are the valency electrons? Valency electrons are the number of electrons in outermost orbital, that is 2p1, and 1 is the valency electron. And as the outermost subshell is 2p, then we say that this is p block element. This is p block element. See, now with this electronic configuration we can determine many more things, like how many electrons are in outermost orbit, what is the valency electrons, what is the number of valency electrons, and what is the place of this element in periodic table. Now we take some more examples, and then we say that oxygen, whose atomic number is 8, how can we arrange them? 1s, 2s, 2p, and then 3s. 1s, 2s, 2p, 3s. Now 2 electrons in this, 2p can maximum be 6 electrons, but here we are left with only 4 electrons and 3s will not be needed. So this is the electronic configuration of oxygen, and here it is also a p block element, and outermost orbit has 6 electrons, and valency electrons are, number of valency electron is 4. So we can now come to K, potassium, whose atomic number is 19. So number of electrons are also 19. Now here we write the series 1s, 2s, 2p, 3s, 3p, 4s. Now this is the series. Now we write 2 electrons here, 2 electrons here, and here 6, 2, how many? 2, 4, 6, 10, 2, 12, and then only 7 electrons, but here it is 6, and 2, 4, 6, 10, 2, 12, 6, 18, only 1 electron is left. So this is the electronic configuration of potassium, and here the number of electrons in outermost orbit is 1, and it is s block element, and valency electrons are also, number of valency electrons are also 1, because the maximum number is 4. So we will see the fourth number of electrons in fourth orbital. Now there are some exception to the Aufbau series. What are these exemptions? See, first exemption is chromium, whose atomic number is 24. Here let us first we write what should be the electronic configuration. What should be the electronic configuration according to our series? First 1s, then 2s, 2p, 3s, 3p, and then 4s, 1s, 2s, 2p, 3s, 3p, 4s, and then 4p. After 4s, there is 3d. After 4s, there is 3d. Now we write what should be the electronic configuration of chromium. Let us see. It is very interesting thing to know that 2 electrons will come here in this orbital, then 2 electrons in s2s, then 6 electrons in 2p, then 2 electrons again in 3s, 3p6, 4s2, and how many left? 2, 2, 4, 6, 10, 12, 18, 20, and then 4. But this is not the case. It is instead, this is written as 1s2. Experimentally we have found it is electronic configuration is 2s2, 1s2, 2s2, 2p6, 3s2, 3p6 and 4s1 and 3d5. Why? This is correct. But why? One can say that the S can accommodate 2 electrons, then why it is 1? See, D has, due to more stability, of 3d5 than 3d4. How? Let us see how. See, these are the 5 orbitals. 1, 2, 3. Let us make it in a fine way. These are the 5 orbitals of D. Then first electron will go to this orbital. Second electron will go to this orbital. Third will go to this, and fourth will go to this. But this orbital in this here, this orbital remain unoccupied. So to make it more stable, the fifth electron will move from here to this orbital and fill this orbital. It will then be 3d5, and this is due to more symmetry of distribution of electrons. This is more stable and lower energy, so this electronic configuration is preferred, and it is experimentally found that electronic configuration of chromium is this. And one more exception is copper. Its atomic number is 29, and hence electronic number of electrons is 29, and if we arrange them in the order, then 1s, 2s, 2p, 3s, 3p, 4s, 3d, then it should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, how many? 2, 4, 12, 18, 20, and then 9. But again, this is not correct. What the correct is, it is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1 and 3d10. Why? This is outermost orbital. This one electron shifts from this to this to make it fully occupied. See, these are 3d orbitals. Then the sixth electron will come here, seventh will come here, eighth will come here, ninth will come here, and the 10th electron will shift from 4s orbital to 3d, and this will be paired, and so due to symmetry it has more stable configuration, and the electronic configuration of copper will be given by this electronic configuration. And another exception is palladium, which has 46 atomic number of electrons are 46, and it has all the 4d10 instead of 5s. There are 4d10 10 elements, for the 10 electrons, the 10 electrons all goes to it. According to our series, it should be 5s2 4d8. But if we count the series from initial series, and we reached up to this 5s2 4d8, but this is not correct. So what happens, this 5s electrons, they come to this and they make it 10, and all are d orbitals, d subshell. In the d subshell, all the orbitals are paired, and hence there is due to symmetry, this has more stability, 5s 0. So there is no electron in 5s orbital, but all the electrons, all the 2 electrons goes to 4d and it becomes 4d10. So palladium has electronic configuration as 4d10, as there are this is called d block element, and in its outermost orbital there are 10 electrons. So this is the way it is electronic configurations are calculated, determined, and all other most of the elements can be arranged in electronic configuration in this series as per their atomic number. Thank you for watching the